And who else is back there? All right. And the OPPO team that's back there taking care. All right. Okay. Good evening, everybody, and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers of the Office of Public Outreach, and it is my pleasure each and every month to welcome you, or at least the months that I'm not traveling. Tonight, we have a lithograph of the pillar in the Carina Nebula. This is one of the early release observations from the Servicing Mission 4 back in 2009. So I guess it's been 8 years. Wow, it's been 8 years since Servicing Mission 4. If you would like to learn about it and see an infrared version of the same image, you can read about it on the back of these. They're available on the two tables. Please grab one on your way out if you didn't get it on the way in. Our speaker tonight, Priyamvada Natarajan, Mapping the Heavens, the Radical Scientific Ideas that Reveal the Cosmos. And as I've told you the past couple of months, I'm really excited because we have no budget for this lecture series. And when I can get someone to come in from Yale, it's absolutely fantastic. So getting an out-of-town guest is a special treat. Please make her feel welcome tonight. Next month, we have Lauren Corliss from Johns Hopkins, and she still has not told me her title. I sent her email yesterday, and I haven't gotten a response. So the topic is to be announced, but she assures me, yes, it's on her calendar. Yes, she's going to give a talk. Some people take a while. They want to wait till the last minute. They don't want to commit too early to a topic. But Lauren will be speaking next month. In April, David Law will be talking about integrated field unit spectroscopy. And I know that sounds geeky, but it's a really exciting field in which we're opening up new frontiers in astronomy. Maybe I'll have him come up with some flashy titles that'll hide the fact that it's about a technology that is just going to it really does change a lot of what we can do in astronomy. It really takes us out into another dimension in astronomy. In May, Mia Boval, she gave a talk last year, and she'll be coming back. She was a very good speaker, and she's talking about the Harvard computers and the HR diagram, where the word computers should be in quotes, because these, of course, are the women who processed the spectra up at Harvard, okay? And they were called the Harvard computers, okay? All right, if you would like to find out the information, you can go to our website. If you just use your favorite search engine, Hubble Public Talks, you will find us. It has a list of the upcoming lectures. It has links to watching it live or watching in the archive on YouTube or via the STSCI webcasting. And you can also sign up for the announcements, the once or twice a month that reminds you of the upcoming lecture, okay? Those announcements, you can sign up at the website. You can also sign up at maillist.stsci.edu, but why would you? It's so much easier to go at the website. Or if you are really lazy, you can just walk up to me tonight and hand me your email address, and I'll make sure it gets added. All right, we have lots of ways for you to find out about this. Actually, since we added it to the website, we have like over 300, 400 people on our mailing list now. It started out as like being 70. All right, so there's lots of people who are finding out about all these talks, and I'm very pleased to say that we're growing by leaps and bounds, at least in one dimension. If you'd like to ask questions, if there's something that we are doing wrong or that you have an improvement or there's a question you have for things, you can send it to publiclecture@stsci.edu, and one of us will get back to you with a response. Our social media, as usual, Hubble is available on Facebook, two, not one, but two Twitter feeds, Google+, Pinterest, and maybe some others that I don't know about. Myself, I have a blog on Hubble site. I'm on Facebook, Google+, and Twitter, although as I caution every month, I only do that once or twice a week because I got so much other cool stuff. There's so much cool stuff in the universe, it's hard to get to Twitter as often as some other people get to Twitter. I don't know why. At least I have more important things to do than Twitter all the time. All right. The observatory will not be open tonight because it is cloudy. I'm sorry. If you looked up and you saw the moon, you saw a nice haze around the moon. So the Maryland Space Grant Observatory is, however, available if you go to md.spacegrant.org. They have observing sessions most every Friday night. Please check their website and get over and enjoy it. All right. So now my favorite part, news from the universe for February 2017. Our top story tonight, only the shadow knows. The older folks in the audience get this, okay? The young kids like you, no, you have no idea what I'm talking about. All right. But maybe you still won't have an idea after I'm done with this, but it's all right. So what we're talking about here is this amazing. Oh, can we kill the down can lights? This is we need darkness on the screen here. There we go. The ones that are shooting down on top of me, just kill those. Nobody needs to see me, okay? Just they need to see the screen. All right. So this is absolute amazing image. This is TW Hydrae. This is a disk of material around a almost sun-like star. It's a 0.8 solar mass star here, okay? TW Hydrae. And this is a disk of material around this young star. This star is about 10 million years old. And what you see in this disk, you also see grooves, sort of like a phonograph grooves, which of course the kids don't know either, but these are gaps in the disk around it. And this is from the Atacama Large Millimeter Array, otherwise called ALMA down here. And using millimeter wavelengths, they're able to see disks of material around these young stars. And in these disks are where we expect planets to form, okay? So we're getting amazing views of planetary systems in formation, not only from Hubble, but also from this millimeter array. And they were able to get the highest resolution ever of a protoplanetary disk when they looked on the interior, and they tell me they're seeing details as small as 1 astronomical unit. And 1 astronomical unit is the distance between the sun and Earth, okay? So they're getting resolution of another solar system down to the scale of the sun-Earth distance. This is really, really cool, okay? So ALMA has been doing some amazing things. They released another one that was really wonderful, HL Tauri, is it called? Oh, I can't. Yeah, HL Tauri, which blew our minds. This one is even a little bit, because it's a little closer, is actually slightly higher resolution. All right. They also were able to last September announce that they had evidence that there might be a Neptune-sized planet inside this gap. There's a gap here that's about 22 astronomical units away from the center, from the star. Neptune, by the way, is 17 astronomical units. And that there might, due to the characteristics of the dust, there might be a Neptune mass planet. They can't say for sure, all right? So TW Hydrae is a really interesting system, okay? Matter of fact, one astronomer said this: TW Hydrae is quite special. Is the nearest known protoplanetary disk to Earth, and it may closely resemble our solar system when it was only 10 million years old. Now that's some cool stuff to study. So of course, lots of people have been studying it, okay? And Hubble has looked at it. Here is Hubble's image from 2016 up against the ALMA image. Now I do this on purpose to show you that we're so used to Hubble having the best resolution, right? Well, it has the best resolution of any visible light telescope. When you go out to these large radio arrays, which can be huge and spread across multiple dishes across kilometers, they can actually get better resolution than Hubble can. So the millimeter array of ALMA actually has better resolution than Hubble does. But Hubble is, of course, looking at visible light. They're looking in millimeter. And so Hubble has been looking at this for several years, trying to determine, do we have evidence of planets in formation in TW Hydrae? All right? Well, here is a 2015 image, and here's a 2016 image. And the astronomers who've been studying this for years noticed that there's sort of a darkish region here, and then there's also a darkish region over here. So they specially processed it to try and pull out the contrast to see those darkish regions. And what they found was that this darkish region here sort of rotated uniformly across to here. Now, the idea here is that it doesn't depend upon distance from the star. Right? If it were something in orbit, okay, then it would depend on the distance from the star. It's moving uniformly at many different distances, okay? And that it stretches out across here, and it's got a period of about 16 years, okay? If you just take this motion over the course of 1 year and extend it out, it would actually rotate all the way around the star in about 16 years. Right? That can't be something out at this 60, 70 AU distance. It has to be in something really, really in close. So what they think they are seeing is the shadow of a tilted disk down in the center, a shadow across the outer disk from a tilted disk in the center. And here's an artist's illustration of that. Yep. Oh, I'm using the wrong clicker. There we go. All right. So this is not to scale. This would be a disk way down deep, around 1 AU in size, okay? And if there were a planet tugging on that, etc., with that to pull it out of alignment, then the shadow from that disk, probably not as tilted as shown here in this artist's illustration, would actually extend across the outer disk. And if there's a planet there to precess that disk, okay, as that disk precesses over 16 years, that shadow will move across the outer disk. All right. Again, this is an explanation based upon the data. We don't have proof of this yet because even ALMA can't see down below 1 AU. All right. So this is the supposition is that there is a 1 AU, but it gives us something really cool to shoot for in this nearest of protoplanetary disks. So who knows what planets lurk in the heart of TW Hydrae? Only the shadow knows. Yes, I really said that. All right. Number 2, our second story tonight. A smidge or two of dust, gas, and star formation. So when I talk about smidge, it's in capitals, so you know it's one of these science acronyms. And this science acronym stands for the Small Magellanic Cloud Investigation of Dust and Gas Evolution. Yes, we scientists come up with some tortured acronyms, but you know, it helps us be able to differentiate our projects. All right, so this is the Small Magellanic Cloud, okay? And you can see some bright gas in here, these red little nebulae. Those are bright gaseous regions, okay? And you can see that gas. But what about the gas you can't see, all right? And it's really important, that gas that you can't see, all right? The gas and dust in these galaxies changes our views, and we want to understand it. We want to be able to characterize it. All right, so how would you see the dust in this room? There you go. All right, you might be able to see the dust in a room in a sunbeam, right? This is a dusty workspace, and you can see that if I look most anywhere through the room, I'm not seeing the dust. But the sunbeams come through the windows, and it illuminates the dust. What's actually happening is the dust is scattering the light of the star. The star happens to be our sun. The same thing is happening in the Small Magellanic Cloud. The light from the stars in the SMC is getting scattered by the dust in the SMC, and actually the blue light is scattered more than the red light, so the red light preferentially is let through. This produces something we call reddening in astronomy. So the stars appear a little bit redder due to the scattering due to dust. And the amount of that reddening tells us how much dust there is. So this is what the SMIDGE project is doing. They're using Hubble to examine this region, which looks small, but it's actually really large for Hubble, to examine this region inside the Small Magellanic Cloud to try and measure the reddening. All right, so here are the geek diagrams. Here you can see that it's a lot of pointings of Hubble, right? Here are all the various pointings of Hubble, and they're using 7 different band passes from the near ultraviolet through visible light all the way into the near infrared. Many different band passes, and the reddening has a certain spectral signature across those various band passes, so they're able to pull that out and separate it out from other effects to truly understand this. Now you say, okay, well, who cares how much dust is in the SMC? Well, it's really important because we use the SMC, the nearby galaxies, as a proxy for trying to estimate how much dust are in the distant galaxies we observe. So this is a standard for all the other studies that we can't do this on, right? So the SMIDGE project is going to get us some really good measurements of reddening in a nearby galaxy and will help improve our observations of all the other galaxies. Now you may ask me, well, what are the science results of SMIDGE? And they haven't come out yet. This press release that I'm going to talk about today was actually done in December, and the first results came out a little bit at the AAS meeting in January. So the press release wasn't even on the results of SMIDGE, but I thought it was really cool that you should know about how astronomers do these big projects with Hubble and what they do them for. The press release itself, well, it was actually to go into the Small Magellanic Cloud, and let me play the movie. All right, so in the constellation of Hydrus, we go into the Small Magellanic Cloud, and this is a dwarf galaxy around the Milky Way. It's a satellite of the Milky Way. And we're going to zoom in, and we're paging through various data sets, and now we get to the Hubble data set finally, and zoom in, and what we find is this gorgeous nebula here. And so that's what our press release was actually about in December. As you may remember, we always do a July 4th fireworks press release. We always do a December holiday lights press release. This was our holiday lights press release, our festive lights. But as I said, it's a smidger too, because this is the nebula NGC 248, but it's not actually a single nebula. One of the cool features of this is it actually has one H2 region, star formation region up here, and another star formation region down here that happen to be lying along the same line of sight from our view. And they appear as if they are a single nebula, but it's actually two star forming regions. I don't know if they're actually connected, but they're very close along the line of sight of NGC 248. So although I started off talking about dust and everything, this is really just a talk about the press release was really just a pretty picture release of the holiday festive lights from NGC 248, our pretty picture for December 2016. All right, okay, that is our news summary, and our featured speaker tonight is Dr. Priyamvada Natarajan, and she's a professor in the Department of Astronomy and Physics at Yale University. She is a theoretical astrophysicist who studies gravitational lensing and black holes, involving the distribution of dark matter in the universe and how light bends around unseen objects as it travels from distant galaxies to Earth. She's the recipient of many awards and honors, including a Guggenheim Fellowship, a Radcliffe Fellowship, and she's a fellow of the American Physical Society, and you said you're going to be the chair of the astronomy
Division of Astrophysics.
Division of Astrophysics for the American Physical Society. She's also a fellow of the Royal Astronomical Society and one of my favorites, the Explorers Club. She has done a lot of work in public outreach as well, being on the advisory board of Nova Science Now, writing for scientific journals, newspapers, magazines, and she has a book published. She also tells me that she has published a collection of poetry. And when we first met this evening, it was not our first meeting. She reminds me that we met in Cambridge, England, 26 years ago. You haven't changed a bit, okay? 26 years ago, we met when we were graduate students, and we were both in England. I was in England while my professor was on sabbatical. So it's always interesting to see how what goes around comes around. Really great to meet you again. Ladies and gentlemen, Priya Natarajan.
Thank you so much, Frank. Yeah, I think you moved some of my slides around. Yeah. It's 3, I think.
There we go.
Okay, so first, I wanted to say thanks for the invitation to have the opportunity to come and speak here. I'm a friend of the Institute, and I've come here a lot of times to talk about science, and this is the first time that I'm actually going to be giving a public talk, also about the science, but talking to you a little bit more about this book that I just wrote, which was published last year, and explain to you why I'm interested in talking about sort of the latest discoveries in cosmology and the history of cosmology over the last 100 years and what's really special about the last 100 years. So first, I want to say thank you to all of you for turning up, because Frank warned me, and he said there may be 20 people in the room today because it's bad weather, and actually turns out there was bad weather for me coming out of, it took a while for the plane to get de-iced, but I was a little nervous, but I made it. So in addition to my training in theoretical astrophysics and physics and mathematics as an undergraduate, I was very interested in philosophy. And in particular, I was interested in the history of ideas. And cosmology was always a little troublesome, intriguing from the epistemology point of view. So if you look at all the other sciences, you can perform controlled experiments. So you can redo, you can replicate. And we've all sort of have a sense that that is part and parcel of the scientific method, the ability to replicate and do repeated experiments. Of course, with the cosmos, we don't have that luxury. So you have a supernova that goes off there, that's what you have. And we have one universe in which we can make experiments. So I always found that intriguing. And in fact, I started a PhD, now aborted, in history and philosophy of science. And I realized I was really much more in love with science than sort of trying to understand. However, my training leads me to think more deeply about the work that I am doing and the lineage of the ideas that I'm working today at. So I decided that the time was right to write a very particular kind of book. I'm very interested in the public dissemination of science because I think that the current rampant disbelief in science stems not from a lack of understanding of science, but a lack of understanding of the process of science, how scientists actually work, what it really means to do science, how you confront new ideas all the time, and how even as scientists we push back, even though part of our training is to be open-minded. When new radical ideas are proposed by our colleagues, we often push back. And it's only the preponderance of evidence and incontrovertible evidence, lots of data, that eventually causes us to change our mind and be open to a new idea, a new worldview. And so I wanted to reveal that process because I think that a lot of my colleagues do a wonderful job in making the latest discoveries really accessible to the public. But I think where more of us could do work is to demystify the process of science. So that was sort of the motivation for me to write this book. And so I want to start with a quote from one of my favorite philosophers. Bold ideas, unjustified anticipations, and speculative thought are our only means for interpreting nature. Those among us who are unwilling to expose their ideas to the hazard of refutation do not take part in the scientific game. This is Karl Popper. So, as I said, my interest has really been in training the lens on showing how science works and thinking about this process while I'm engaged in research. And in particular, I have been interested in the human, the emotional, the psychological side of science, because I think very often the image of science that is presented as this sort of very objective activity where people in lab coats are teasing out secrets from nature is a little bit misleading, because at the end of the day, science is a human endeavor. We are human beings, and it is laced with subjectivity. And it is driven by passions. And scientists always write their passions out when they talk about the discoveries, right? And I wanted to bring to the fore some of the sort of the rivalries, the confrontations, the personal ambitions of people, of the scientists, behind some of the greatest ideas of the last 100 years. And in particular, as I mentioned earlier, I'm interested in the arc of acceptance of any radical new idea. And the reason for focusing on the last 100 years is that they've been transformative for cosmology. And it's been this incredible interplay of ideas and instruments over the last 100 years that have completely transformed our cosmic view. So in 1914, right, our view of the cosmos was restricted only to our galaxy. We did not know if there were other galaxies. So we thought the Milky Way was alone, stagnant. It was the only thing in the universe. And eventually, the astronomer Edwin Hubble showed that there were other nebulae. These smudges that you saw in the night sky were actually external galaxies. So our cosmic frontier has gone from there to today, where we know we have relic radiation from the Big Bang, and we actually can plot the timeline of the universe from when it was 400,000 years old to today. So it's been spectacular, the progress that we have made. And I think it's the particular, of course, driven by human curiosity, but the particular powerful confluence of ideas, instruments, and computers more recently. But one other aspect about understanding our place in the cosmos and the cosmos itself is intricately related to the idea of mapping. So since the first human beings could stand up erect and gaze at the night sky, we've been intrigued by the night sky. Well before we had theories, ideas, conceptions, causation, laws that describe the cosmos, we were charting the cosmos. We just wanted to know. We wanted to know why there were these regular phenomena in the universe. And I think that one interesting way to see the history of the unfolding of the history of our understanding of the cosmos is through maps. And I have a personal stake in maps because when I was growing up, I grew up in India, but I lived in the US most of my life, partly in England. And when I was a child, I was fascinated with maps, both terrestrial and celestial maps. So I would always have my head with these atlases that I could barely lift when I was a child. And I think that maps for me are very evocative, both literally and metaphorically. So literally, there are obviously the maps of the sky, maps of the early voyages of terra firma. But maps also stand in for me as metaphors because they codify our current understanding at any given time. And as we have new knowledge, I think we remake our map. We remake our cosmic map, just as we remake our worldviews. And I like this kind of, this idea of mapping because it's also related to our receptivity to new ideas and our desire to know more and to be open to unknown frontiers. So in the book, I talk about maps both literally as well as a metaphorical device. And I look at the arc of acceptance of ideas, and I focus, as I said, on the resistance from within the scientific community to a whole bunch of radical ideas. The idea of the discovery of the expansion of the universe, the discovery of dark matter, the discovery of dark energy, the discovery of other planets around other solar systems around other stars potentially, and now even the idea that there might be other universes out there. So there's been a huge number of radical ideas that have been proposed, and I wanted to focus on the resistance from within the scientific community to those ideas when they were initially proposed. And I wanted to show how these ideas actually became accepted, right? And so I do sort of these case studies. But before I move on to, today I'll talk about two radical ideas, and I'll sort of take you briefly through the history, but bring you to a state of the art as to where we are, the idea of dark matter and the idea of black holes. But before that, let me show you why I like this notion of maps. So this is the earliest depiction of the night sky by any humans that we know of. This is the Nebra sky disk. And notice that it dates back to 2000 to about 1600 BCE. So what we believe that this depicts is the sun, the moon, perhaps the Pleiades cluster. And of course, the Mesopotamians were the inveterate mappers of the night sky. So this is one cuneiform tablet that was discovered which notes down. So by the way, this script has been deciphered, right? So this is why we know what it is. These are the positions of the planet Venus that they recorded. So these guys were recording. So I think, first of all, it's incredible to realize that they knew the difference between planets and stars. And then they were actually recording the positions of Venus. Right? And coming back to my idea of the refinement in our understanding and how that's depicted in maps, this is one of my favorite maps. And this is a map, an illuminated map from about 1375 or so, in which now we had human beings at this point, right? So we didn't have a conception of laws and causation quite. So we didn't have Kepler's laws, we didn't have Newton's laws. This was well before all of that. But notice what you have, they were these regularities of night and day. And the way people made sense of it at this time was that you have these two angels that are turning the crank. And this is how you're getting night and day. And this is how you're getting seasons, right? And then, of course, Copernicus comes along and he shifts the pivot from the Aristotelian and Ptolemaic idea of the cosmos to our current view. And he moves the pivot from the Earth to the sun. So up till then, the whole idea was that the Earth was immovable and it was static, right? And so Copernicus just shifted the pivot, moved the Earth and sun, swapped their locations, and argued that in our solar system, the planets revolved around the sun. There was a lot of resistance to that idea, right? And as it happens, even in modern cosmology, for a radical idea to be accepted, oftentimes there's kind of like a halfway house, dodgy sort of idea that is a little more acceptable, that's sort of a stepping stone before people buy in the whole radical idea. So here is a depiction of the Copernican cosmos that is slightly older. So Brahe, Tycho Brahe, he was sort of the last great naked eye astronomer. And he had a model that was sort of a halfway house model. So basically the idea was that, yes, a lot of the other planets moved around the sun, but the sun itself moved around the Earth. So before you could completely change the pivot, this was sort of a halfway house model. And so what is depicted here is the Urania, the muse of astronomy, kind of weighing these two models. And notice here, the one-eyed Argus is holding a telescope. So this is 1600. Galileo has already repurposed the spyglass, and it is now bringing into view all kinds of new phenomena, right? And you can see sitting in the corner there, discarded model of Ptolemy, and sort of the old man sitting in that corner with his discarded model. Right? So through these kinds of maps and diagrams, we can see how our cosmic view got refined, how it shifted, and this is where we are today. Right? So today we know about the cosmic history, the origin of our universe, starting from a fraction of a second. We believe that we have a theoretical understanding of how the early universe, which was hot and dense and compact, actually exponentially expanded. And we also have data evidence from the relic radiation during this hot phase of the universe, the cosmic microwave background radiation, when the universe was about 400,000 years old or so. And we also have a theory that predicts, along with some tantalizing evidence, for when the first stars likely formed. And this is an era, an epoch, a window that JWST is going to open wide for us. So we're all very, very excited to actually start to maybe see the first stars. And we then know how galaxies assemble, and we know the timeline. We know that this entire cosmic story has unfolded over the last 13.7 to 13.8 billion years. On top of that, we also know the cosmic inventory. We know what the universe is composed of. And here we have some intriguing open questions. We know that the inventory of the universe, the total matter content, is dominated by dark matter. This is matter whose nature still remains elusive. We know it's matter, it exerts gravity. We know it does not emit light, does not reflect light, but it deflects light, as we will see. And the bulk of the energy content of the universe is dark energy, and we don't know what it is. We know it's there, so we see the indirect effects, so we know that this is the composition. And the stuff that we are made of, all the ordinary atoms in the universe, everything in the periodic table, is a measly 4% of the cosmic inventory. So all of this we know, and we have many, many independent lines of cosmological evidence that has given us this inventory. So what I want to do now is to basically talk to you about two radical ideas, two of these radical ideas, the idea of dark matter and the idea of black holes. And they're somewhat similar in the sense they're both invisible entities. They're intriguing, and they have been indirectly mapped. We know of their existence. We don't know their true nature quite. So I'll talk a little bit about how they were discovered and how they actually became real. And the reason I say they became real is because they're invisible entities. And in medieval times, we had a lot of these invisible fluids. We had phlogiston, we had miasma, we had ether, and all of these vanished. And what I want to show you is that these invisible entities are here to stay. And the reason for that is the kind of observational evidence that we have. So first, let me take you through a quick journey of the history of the idea of dark matter and where we are at the frontier today. So the main evidence for dark matter comes actually from the effect that dark matter exerts on the motions of stars, the motions of galaxies. And we also know about the existence of dark matter from the impact that it has on light rays. And as I said, the presence of dark matter in the universe actually bends light rays. The presence of all matter bends light rays, and the amount of visible matter is insufficient to explain the kind of deflections that we see. So the proposal for dark matter originally came from this cantankerous Swiss astronomer, Fritz Zwicky, when he was working at Caltech in the 1930s. So this is an image of the Coma cluster. This is a cluster of galaxies, which are about 1,000 galaxies that are held together by the invisible grip of gravity of the dark matter that you don't see. And because there is dark matter here that you don't see, the only way to infer that it's there, at least Zwicky used the motions of these galaxies, they were moving much faster than you would expect if the only gravity in the system was provided by the stars that you see in the galaxies. Right? So whizzing around much faster. And so he proposed that perhaps what you have is you have a lot of unseen matter that's providing gravity that is causing the motions of these galaxies in this cluster to be so much more faster than you would expect. And that was in 1933. In 1937, he also realized that if there was copious amounts of dark matter here that we don't see, this dark matter should cause deflections in light rays of distant galaxies that lie behind the cluster. And he said it should be measurable. So in 1937, we did not have the equipment to make measurements of the deflection of light. But he calculated that as and when we did have instruments with the required degree of accuracy, we should be able to measure light deflections. So he proposed, so there's sort of these two different ways in which he proposed for the Coma cluster. And what's interesting is that this idea that the presence of dark matter affects the motions of bodies has to do with Newton's laws. This is just Newton's laws of gravity. Whereas the light bending actually is a prediction of Einstein's theory of general relativity. So what is compelling here is that whether you want to live in a Newtonian universe or in an Einsteinian universe, either way there's no escape from the need for dark matter. So two completely different lines of thinking, completely different conceptions of cosmos, conceptions of laws, gives you the same amount of dark matter in this particular class of objects, which are clusters of galaxies. So there was further evidence. So the idea of dark matter kind of was around. It was too radical. It sort of fell off the wagon. And as with a lot of radical ideas, it had to be invented, reinvented, rediscovered, reinvented. And the most compelling case was made by Vera Rubin and Kent Ford. And as you all probably know, we lost Vera earlier this year. So what she did in the 1970s, she was doing a very similar exercise to what Zwicky was doing, except she was looking at the speeds of stars around an individual galaxy rather than the motions of galaxies around the cluster. And what she found was, once again, the stars were moving much faster than you expected if the only gravity was being provided by the matter that you see. So this is what you expect. The red curve is what you expect if the gravity is provided only by the visible matter that you see in the galaxy. So this is measuring the speeds of stars as a function of distance. So this is called a rotation curve. And what is measured is that white curve. And as you can see, something appears to be holding up the galaxy, as it were, at very large radius, providing gravity, very, very large radius, even at distances where you sort of run out of visible stars, and basically you have dust and gas, and you notice that the rotation curves are flat. So this was a pretty radical idea, and they actually held back from publishing it for a couple of years till they collected a lot more data, many spiral galaxies, before they published this idea. So just to give you a feel for why this is so peculiar, so let's just come back to our solar system and look at the motions of the planets around the sun. The sun is the dominant gravitational body in our solar system. Oh yeah, I sort of went to school when Pluto was still a planet, and I'm emotionally attached to that. So this is a radical idea that I am not willing to give up quite yet. So there are 9 planets. So if you look at the rotation curve of the solar system, which is the speeds of the planets as a function of distance from the sun, because the sun is the gravitationally dominant body, you see that as you go further out, the speeds fall very dramatically. It's because you're moving further and further away from the sun, and the force of gravity falls off as 1 over r squared. So that would be the shape of the rotation curve. So remember, when you do the same exercise with a galaxy and you start measuring the speeds of stars around galaxies, instead of seeing a declining curve, you are seeing something that looks completely different. Okay? So this is the evidence for dark matter, and and this is just not a one-hit wonder. There are many, many galaxies, and now we know pretty much every galaxy in the universe has this extended dark matter halo that provides additional gravitational material. So it's just that we don't know. We know that about 90% of the total mass, give or take a bit, for most galaxies is actually dark, and only a small portion is visible matter that we see in gas and dust. So just to give you a contrast, right? So this is why this is such a radical idea. But anyway, we have accepted this idea now. In fact, this is our standard framework. We kind of know the kind of dark matter particles. We think these are cold dark matter particles that move very sluggishly in the universe, that don't actually collide with each other. They're collisionless. They just go past each other, and they are bound by gravity. They aggregate in the universe. And this is our conception. This is my cartoon of what we believe a typical galaxy to look like. So the stars that you see in the center are a very tiny portion, and most of the galaxy remains unseen. So let's look at the other method that was used to establish the presence of dark matter, and that's the discovery of light deflection. And this was actually predicted by Einstein's theory of general relativity. And remember, Einstein fundamentally reformulated Newton's conception of gravity. So remember, for Newton, gravity was divinely ordained, and it was a property of masses, and you have 2 bodies with masses. They felt the force of attraction. This is not what Einstein believed gravity was about. He radically reconceptualized gravity because he had this profound insight where he was able to link geometry to physics. So he conceived of the universe as a 4-dimensional sheet called space-time, and he believed that what mass is the attribute that causes divots or potholes in the fabric of space-time. The universe is space-time, And the presence of masses in the universe causes these little potholes. And since there's nothing above the universe or below the universe, light has to travel on this crinkled fabric. And every time light from a galaxy encounters a divot, it gets deflected, right? And so Einstein actually predicted that, and in fact, he predicted that during an eclipse, so this is what made him a superstar overnight, the actual experimental verification of this prediction of general relativity. We'll see about the next prediction that he made, which was verified last year, that of gravitational waves from merging black holes, also a prediction of theory of general relativity. So here, during a solar eclipse, when the sun and the earth line up, you can imagine the divots are the deepest when things line up, and the positions of stars appear to be displaced from where they actually are because of the deflection of light rays, right? And you can actually, general relativity actually predicts, and when you no longer have an eclipse, you can go back and see where the stars really are, what their distances are, and you find that it's modified due to an eclipse. Now, as I mentioned, the divot or the pothole that is generated in space-time depends on the mass. So if you have a cluster of galaxies in this cartoon, we have a cluster of galaxies, and notice that it causes a very deep divot in the fabric of space-time. And so you have a lot of extreme light bending that is produced by the cluster. The effect that Fritz Zwicky predicted should be observable is observable. And in fact, although they were ground-based observations, it was the Hubble Space Telescope that has completely transformed our understanding of lensing, allowing us to measure very, very accurately and in detail the distribution of dark matter that causes this amount of light bending. So for example, this is the bent shape of a distant galaxy that is lensed by intervening matter, primarily dark matter, around an individual galaxy. So you have a distant galaxy, which in reality is a little blue smudge. And you have in between, along the line of sight to us, another galaxy that's just lined up with its huge dark matter halo that distorts the light from that galaxy and stretches it out into that arc. Okay, so this is the Hubble Space Telescope image. So this is a schematic to explain this a little bit better. So when you have a cluster of galaxies, you're causing this huge divot, and you have deflection of light rays from, so these are distant galaxies that lie beyond the cluster on the line of sight to us. And depending on the distribution of what we know now is primarily dark matter, depending on the shape of dark matter, you see a whole bunch of effects. So these are all Hubble Space Telescope images. Okay? So these are seen now. We can measure the deflections, and we can quantify, we can back out, and this is what a lot of my own research has been, figuring out the methodology to look at this image with the theoretical conceptions that we have for how dark matter might be distributed in a cluster of galaxies, back out from this image what the actual distribution really looks like. And in particular, I have focused a lot on trying to get the granularity of dark matter, because there might be a clue to the nature of dark matter in the granularity of the spatial distribution and the clumping. That's what I mean by granularity, how clumped it is, how clustered it is. So nothing is actually moving in the universe. This is just an animation to show you the kinds of lensing effects, the distortions that you could potentially measure when you have a cluster. So the cluster, the mass of the cluster, the projected squished mass of the cluster is shown in red. And what you see in the background, these blue galaxies are actually little circles, which are behind the cluster. And lensing causes their shapes to be systematically distorted. And for the galaxies that line up behind exactly the center of mass of the lens, you see the most dramatic distortions. You see these extended arcs. And occasionally, depending on how massive the lens is, how much dark matter there is along the line of sight, if you imagine a light ray to be a tube, occasionally you can split the tube into two. So you end up seeing 2 images, 4 images. You actually end up seeing 3 images, but you see, 2 bright images and 1 demagnified image of the same object. Okay, so here's an example from the Hubble Space Telescope. We see 5 images of the same background galaxy that looks like a bicycle wheel. Okay? And notice that that's where you see them. And there's a fifth image in the center, which is demagnified. So there's a theorem that tells you you always have an odd number of images. So you have 4 magnified images. And the reason we know they are all images of the same single object is because they have the same spectrum. So remember, the spectra are basically fingerprints for galaxies. And so we know. Once again, Hubble Space Telescope has radically transformed our understanding of gravitational lensing and mapping dark matter. This is a very, very famous image of this cluster called Abell 2218. And here you see by eye, now you can all pick up the lensed galaxies. These are all stretched out. You saw the animation, so you can see. And so by eye, you can already tell that although these are the members of the cluster, so these are cluster galaxies like the ones that Zwicky saw in Coma, what we now know is there's a huge amount of dark matter sitting here that's unseen because of the distortions that are produced in background galaxies that lie behind the cluster. So the question is, why is this interesting? And why are we interested in the granularity, the distribution of dark matter? So this is a simulation from one of my colleagues, Jörg Diamant. And what you see here are actually dark matter particles. They're mocked up to look like light, but these are all dark matter particles, which have the nature that I talked about earlier. They're collisionless, they're cold, they only interact via gravity. There's no charge, there's no other interactions. It's just gravity. They just assemble by gravity. And what we are seeing is a slice that shows the assembly of a cluster of galaxies like the one we just saw. So notice we're just zooming through it. So this is the cluster. And what you see is there is a large fuzzy dark matter halo. And there are many individual little dark matter halos which are associated with the galaxies that are in the cluster. Okay, so this is the, yeah? Because it's cold dark matter that doesn't collide. So in order to collapse, it's pressureless. You need pressure and you need to collide. There's no friction, there's nothing. They sort of go past each other. It's very peculiar, but this appears to be the best equation of state, pressure equals 0, which describes the bulk of the dark matter in the universe. And so why are people like me obsessed with this sort of the clumping of dark matter? So here is a slice from 2 simulations of 2 different kinds of particles. One is this particle that doesn't collide, that doesn't dissipate, that doesn't have any pressure, and the other one is warm dark matter, which has a different nature, that actually there's a scale below which it doesn't clump. It's much, much smoother. Look at the distribution. So our idea here is that if we can somehow get the best possible data from the Hubble Space Telescope and completely map out the dark matter in detail, then maybe we'll be able to distinguish between these 2 candidates, right? So that's kind of been the quest. So I'll show you a little bit of the kind of work that people who work on gravitational lensing like me have been doing. I'll show you some of my own work. So this is the cluster of galaxies. What we do is we try to figure out, we realize this bunny rabbit is the region. If you look through the bunny rabbit, any galaxies that lie beyond the cluster are going to get multiply imaged. Right? So we do the analysis and we back out this as the distribution of dark matter. So there is a smooth mound of dark matter, and on top of it, there are lots of clumps. So what we can do is we can go then and compare with the theoretical expectation of whether the number of clumps tallies with theoretical expectation, whether the masses of the clumps tallies with what we expect in the universe, and so on. So what has been radically transformative is this brand new data set called the Hubble Frontier Field. So the deepest look that Hubble has taken on 6 of these clusters. They're very massive. They are colliding. They're sort of in the process of forming. So they have highly irregular geometries. So there's a huge amount of dark matter here. And you see a lot of lensing. By eye, you can pick up. There's 200 to 300 little background galaxies that have been mangled in shape that are here in this image. Right? Using that, that's the reconstructed dark matter map. What you see is blue fuzz is the dark matter that is there. that is exerting the gravity that is required to produce the lensing that is seen here. So that's a map of the unseen matter in the same region of sky. So this is from a new paper that we've just put out. This is the detailed dark matter distribution and the clumps in this data, this particular cluster that I just showed you. Okay, so here it is. So from the astrophysics point of view, we are pushing, and we've arrived at, well, I can map the dark matter, I can tell you how it's granular, and so on. And what is incredible is the observational determination of these clumps, which is technically called substructure. It tallies, and it's in very good agreement with cold dark matter, with this peculiar candidate. So the candidate particles are neutralinos for that kind of dark matter. And there have been people who are waiting with detectors trying to detect them directly. No success. Okay, so nothing. We haven't found nothing. And in fact, the experiment, there have been many experiments, Lux and Xenon, we haven't found anything. Okay? So there's one very controversial claim that was made more than a decade ago. And this was an experiment called DAMA, which had a sodium iodide crystal. And the whole idea is, if you think of a crystal basically as springs that are connected, so you have a dark matter particle that goes through that jiggles the springs, and that's what you detect, but you'd have to shield it from all other things that can jiggle the crystal, right? So this was a pure sodium iodide crystal, and there was a claim that they detected a seasonal variation that you should if we are moving along in this sort of dark matter wind that we are surrounded by, that is the halo of our galaxy. So it's a controversial result. Most astronomers and astrophysicists and physicists don't believe it. However, we know that only with replication, right? So very recently, finally, replications of this experiment were funded. So there are 5 replications. The same fabrication technique used to make the same crystal by the same company, and it's going to be replicated in South Korea, in Italy, in Japan, and Germany. So we're going to wait for these results to see whether these results will be replicated. So that's the word. That's where we are with dark matter. And then some of you may have seen that there were recent claims that maybe we don't need dark matter at all. Maybe what we really need to do is change our theory of gravity. So there is no real convincing explanation other than dark matter at the moment. So there's some attempts, but the reason I focused on clusters of galaxies are that there is no alternative theory that can explain the motions of the galaxies in clusters, as well as the gravitational lensing, the light bending that is produced by dark matter in clusters of galaxies. Okay, so let's move on to the next radical idea, and that was the idea of a black hole. So the origin of the idea was kind of interesting when I kind of tracked it down. And it was an idea that dates back to John Michell and Laplace in the 1780s. So this was when light was believed to consist of particles, of corpuscles of light. We did not know, at this time it was not known that light was actually waves. It was believed to be particles. Newton actually thought they were particles. And so if you had a star that's very massive, its gravity would just grab particles of light, and light could not escape from that object. So that was a dark star. So that's sort of the origin of the idea, because the concept of a black hole really hinges around the fact that the black holes appear to have this surface called the event horizon, out of which not even light can escape. So I was very intrigued, being Indian, of Indian origin, to have discovered that the phrase black hole actually does not come from the astronomical object. It comes from, it's an infamous place. It's a prison. It was a prison which was basically a point of no return. So there was the Nawab of Calcutta had captured soldiers from the British East India Company and had put them overnight in the cell, and most of them died. And so there's this prison that was called the Black Hole of Calcutta. And strangely enough, the astrophysical object was actually named after this phenomenon, the point of no return, basically. So what is the black hole? So we can think of the black hole. So when we think of Earth's gravity and when we are launching satellites, we really have to boost satellites to escape Earth's gravity, right? So you can imagine if the velocity with which you had to boost a rocket off the surface of an object was the speed of light. Right, so that's what a black hole is. So that's one way of thinking. There are many different ways of thinking about a black hole, because in a way, a black hole is basically an exact mathematical solution to Einstein's equations. Okay? So it's a peculiar object. It's an object that encloses a very uncomfortable, the reason it's so uncomfortable and peculiar is it encloses this point called the singularity, and that is encased by the event horizon, which is the point of no escape. So once even light crosses the event horizon, it cannot make its way back. Gravity is so intense. So that's one way of thinking about it as a mathematical entity. As an astrophysical entity, we can think of the black hole as basically a very, very dense, compact concentration of mass with intense gravity. So if I think about if I push you back to this conception of space-time, and remember I talked about the sun and galaxies and clusters causing this divot or pothole, a black hole would cause a puncture in space-time. That's how dense, how massive, how intense its gravity is. And so this region, it's called the Schwarzschild radius or event horizon. Not even light can escape. And suppose I had, suppose for the Earth to behave like a black hole, to have an escape velocity that was the speed of light, I would have to condense all the matter in the Earth, the entire matter in the Earth, into less than a centimeter. That's when it would have the properties of a black hole. And if I had to do it to the sun, I would have to squish the sun to about 3 kilometer size. So once again, the idea of black hole, this mathematical solution, came from Einstein's theory of general relativity. And I think what's really beautiful about, one reason, I'm not often for sort of hero worship of individual scientists, and, because obviously I think one gender has kind of taken it over. But however, I think I cannot but gush about what Einstein did. It was very profound insight between sort of this connection between the contents, the geometry, and the fate of the universe, right? The fact that geometry, matter, and dynamics, motion, were related. That was profound insight, okay? And it revolved around this conception of space-time. So this is just to give you a feel that if space-time, there was no matter in the universe, we had an empty universe, space-time would be flat. And if you have the sun, you have the divot or the pothole that's made by the sun. This is a pothole that's made by the neutron star. And a neutron star is much more compact and more dense, which is why the divot is a little deeper. And if you look at the black hole, basically it's a puncture. And this region, this is roughly what we call the event horizon. Okay, so and the interesting thing about the event horizon is, as I said, what happens to light if it grazes past the event horizon? So orbits that actually enter the event horizon never make their way out. There are grazing orbits. There's an orbit where you would escape. And remember, this is the singularity that's in. And the singularity is peculiar because singularity is the place where all known physical laws break down. So that's our limit of understanding. That's why black holes are so enigmatic for us as physicists. That this is where everything that we know breaks down. No laws, nothing. We don't know. We don't know how to think about it. Okay? And so, but there's some interesting orbits of light. There's actually an orbit where light would just be perpetually trapped, like Dante's limbo. Right? One of the other peculiar things, remember it's space-time, I've been talking about this four-dimensional entity where time and space are intertwined. And so weird things happen to the nature of time right around a black hole. So time actually slows down near a black hole. So for an outsider, an observer who is sitting outside, an infalling object seems to take forever to fall in, right? Time slows down. So this is what sort of, so I hope I've sort of given you a sense of how enigmatic and why these objects are so enigmatic. So now let me tell you from the astrophysics point of view what we know and how we know what we know about black holes. So the big challenges about black holes are how they form in the first place. How do you make them? Right? So the reconciling, we know that they're like mathematical solution, but how do you make them? Right? How do you actually compact so much matter into such a tiny, dense object. And the question is, how do we know that every galaxy in our universe appears to harbor a black hole, including our own galaxy, the Milky Way, has a black hole that is 4 million times the mass of the sun in the center. Okay? The question is, how did it get there? How did it become so big? Right. And then, does the black hole itself reveal its presence by doing something, by affecting the galaxy that it's sitting in? Can we get some clue? So those are the kind of open questions. But this is a really hard problem. It's a very hard problem because of the kinds of physical scales that we need to take into account, phenomena on many different scales that need to be taken into account, both computationally or analytically, what have you. So it's really has been a very hard, almost intractable problem, but we've made a lot of progress. And the reason for that is if you look at a million solar mass black hole, like the one in the center of our own galaxy, the event horizon, or the Schwarzschild radius for such a black hole, is about the size of the penny. Say it's the size of the penny, right? Then the full extent of the galaxy, right, the stellar, just the stars in a galaxy, not the dark matter halo, just the stars in the galaxy, it's like the size of the Earth compared to that penny. Okay? So right in the vicinity of this penny, right around the black hole dominates. But as you go further out, the black hole really doesn't account for much in terms of gravity. So when you're looking at the scale where we've been talking about the rotation curves of galaxies, it doesn't matter if there's a black hole or not, given the mass of this black hole. Right? But integrating all the physics that happens on these scales and getting a full comprehensive picture has been really difficult, and we don't quite have it. So what we do at the moment is we do piecemeal. We look at we focus our computations on a small scale, and then we kind of coarse grain it. We do a broad brush, and we look at the larger scale, and then we try to patch our understanding to build up. Yep. Well, it'll get accreted. So it doesn't matter. You know, I think my unmatched socks, which I'm losing all the time in my laundry, are probably unmatched socks go into black holes. The thing about the black hole is that there is no memory of what went into the black hole. Remember, once you cross the event horizon, it could be anything. So indeed, dark matter could be accreted by black holes, but the amount of dark matter that a black hole would accrete would be a tiny trickle compared to the fire hose that is actually gas, as I'm going to show you, in the centers of galaxies. So this is typically where black holes we think reside, supermassive black holes that are about, supermassive is basically anything that's above 1 million times the mass of the sun to 1 billion times the mass of the sun. They're actually ultramassive black holes that weigh more than 1 billion times the mass of the sun in the brightest galaxies in the universe. And so this is a slice of a simulation from one of my graduate students where we are trying to make the first black hole in a computer simulation. We're trying to condense the gas. And the idea here is that we have a model which is an alternative to the standard theoretical model. The standard theoretical way to make a black hole, which we know is verified now, is that you make the first stars in the universe, they burn up all their fuel, then they leave behind, they explode, leave behind a little black hole. If they started life out with a mass of about 8 to 10 times our sun, they will always end up in a black hole. Lighter stars will not end up in a black hole. They'll end up as white dwarfs and neutron stars. Massive stars will leave behind a black hole. But that's a tiny black hole. That black hole would be a few times, few tens, maybe 30, maybe 50 times the mass of the sun. So the question is, how do you go from that to 1 million times the mass of the sun, 1 billion times the mass of the sun, right? So we have an alternative idea. This is called direct collapse black holes, where in the early universe we postulate that you can make a gas disk before you make any stars, pre-galactic. You have a gas disk. Gas is what rules the early universe, so you have a gas disk. And just as the water goes down, when you pull the plug in your bathtub, you see the vortex and water goes down really rapidly. We think you could have an instability in the disk that could make gas swivel down into the center very, very rapidly, condense, and give you a black hole. So we're trying to recreate that idea in our calculations. And we know that in our real universe, we have the appropriate conditions for this to happen. Happen rarely, but it can happen. So here's some more progress about looking at the smaller and smaller clumps that we can start to resolve. And this is showing that this is gas that's falling into those clumps. And we know, therefore, that black holes are really growing by feeding gas. So one of the peculiar things about black holes that we observe in the universe, so we observe black holes. Black hole itself does not emit light, but en route, being sucked in by a black hole, the gas gets heated up to very high temperatures and it's glowing. So you are seeing the dying gasps of these gas particles as they're falling in. And that reveals the presence of a black hole. Once again, it's indirect. Remember I told you with black holes and dark matter, the evidence is indirect, but it's there. Right? And so, however, we see in the universe that black holes come in two modes. They're either feasting, gobbling a lot of gas, and so you see them as bright quasars. Beacons in the universe, they're the brightest objects in the universe almost. You can see them to great cosmic distances, and we are finding them, right? Or, like the Milky Way, you can have a black hole in the center of our Milky Way is dead. It's basically fasting. So it looks like it's sort of black holes binge. They go between feasting and fasting. And the majority of black holes in our universe appear to be fasting. And it's only black holes that are at very, very early times glowing as quasars. So I don't know why this movie is not working. Okay, so this is, I think, the most convincing evidence for, you should go check this out. This is from one of my colleagues, Andrea Getz, who is at the UCLA. This is the Galactic Center group. What you would have seen if this movie had worked, these are stars that are right around the galactic center of our galaxy. This marks the location of the black hole, and you could actually see the orbits come through. This would have been a time lapse, and you could see that many of these orbits actually close into neat little ellipses. And so you can figure out that there's some massive object at the foci of that ellipse, applying Kepler's law, and you know what the mass of the black hole is. And that's how we've inferred the mass of the black hole in the center of our own galaxy. Coming back to feeding black holes, so this is a slice from a simulation where you actually see, you're looking at a cross section, the black hole is here, and you have a feeding disk of gas. So that's fueling and trickling down to the center. Okay? As I mentioned, bright quasars are really growing black holes, rapidly growing black holes that are fed by a lot of gas in the centers of galaxies. And so let me just show you, starting from Hubble data to artist's conception of what we think is going on with black holes. So we're zooming in now. So this is all real data, and eventually we'll move to artist's conception because we can't resolve those scales. Remember I told you the scales. So now this is our current understanding of what's really going on around the black hole. This is gas. This is the gas disk that is feeding the black hole. And you see the black hole there, and often black holes drive jets out that we see as well. And so as we saw last year, the LIGO collaboration actually detected gravitational waves, the shaking of space itself, tremors in space itself, from the merger of two black holes that were about 30 times the mass of the sun. And this was theoretically predicted, and we've been searching for it for 40 years, and finally we had a first detection. So let me now come back to the understanding the growth of black holes and talking about feasting black holes. So how do you actually power quasars? So these are two spiral galaxies. This is a simulation made by one of my former graduate students, Pedro Capello. So two gas-rich spiral galaxies. You don't see the dark matter here. We are showing you only the gas because that's relevant to feeding the black hole in the center. And you see this is a merger of two galaxies. We believe that your structure in the universe is built up largely by these kinds of mergers of small galaxies that give you bigger galaxies over cosmic time. And you see the flickering. Those are feeding episodes. So every time gas reaches the center to the black hole, you see flickering. Right? So we believe that black holes are actually fed dramatically during, they have these feasting episodes, when two galaxies that have central black holes in them merge and a lot of gas is sent to the center, and you see a burst, a sort of a feeding episode, and you see that light up as a quasar. Okay? And these are detected. So I just wanted to show some other sort of interesting Yeah, so gravitational waves, when you detect gravitational waves from the merger of two black holes, gravitational waves, unlike electromagnetic waves, right? So you actually have to detect using those interferometers that LIGO did of the very, very slight stretching of space as the gravitational wave passes through. What would be awesome is if there was some other electromagnetic, if there was an alarm bell or light that went off that said, hey, two black holes are going to be merging here soon. Look here, right? And so we've all been trying to see, because there's a lot of gas, so if there's gas, there has to be other kind of radiation. So this is an early calculation that I did with one of my collaborators. This is a top view of a supermassive black hole that is sitting here. This is sort of 1,000 times the event horizon, this black region. And the black hole is sitting here. And we have plopped a second black hole. This is the zooming in on the inner regions of the movie that we just saw with the galaxies. This is just to bring home the point to you about scales, the cascading, the telescoping of scales. This is zooming in, looking right at the heart to see when the black holes actually merge. So this is the accretion disk that you see in red. This is a top view, so you're viewing it from the top, and you have a massive, supermassive black hole here. You have a second one that's plopping in there. And what you see here is the profile of the disk. So the disk has a profile where it's piled up in the center, but as the second hole is grinding in and falling in, first you may notice this looks rather like one of the images that Frank showed us earlier about the gap. So you're opening up. You have the same phenomenon when a planet is plowing through a disk, or you have a black hole that is plowing through a disk. You open up these gaps. Okay? And you emit a lot of radiation that signals to you, this is a region, this is the center of a galaxy where there is a binary black hole merger, and you will eventually, when this guy makes it in here, you will see gravitational waves. So we're sort of trying to do the calculations for the precursors, the postcursors of gravitational wave detection. No, LIGO is not set up to do electromagnetic. So other telescopes and other detectors. For this particular, I'll just show you. For supermassive black holes, you're going to actually have to do the LIGO kind of experiment in space. And there's a mission that's planned. It's called LISA. I'll just show that's my last slide, actually. So one of the interesting things is that this calculation, this cascading of scales, right, zooming in, and seeing right to the heart of the inner regions of galaxies where these supermassive black holes. So I just want to remind you, LIGO saw the merger of black holes that were about 30 times the mass of the sun. They were not supermassive black holes. And I'm talking really about supermassive black holes here, which is like the next frontier, right? So there was a computational breakthrough which allowed us to cascade and go all the way in. And this happened about 5 to 10 years ago. And without that, LIGO would not have been able to figure out what they saw. So this is coming back to your question. So if you had black holes that are supermassive, the frequency band in which you would see them would be much lower than LIGO. And for this, you would need the same kind of interferometer in space. And that is proposed by the Europeans. It has been proposed. It's called LISA. And the Americans have been wavering about joining. They joined, they pulled out. They're going to join, hopefully now, with the LIGO detection. So this would be the most exciting discovery, and I hope it happens in my lifetime. Really waiting for that window of gravitation, looking at the gravitational waves from merging supermassive black holes. So let me just close here, but by trying to persuade you and show you why people like me are doing what we do in the context of these particular ideas about unseen entities, right? What are we actually trying to do? We're looking for gaps. We are looking for a mismatch between our theoretical expectation and an observation, right? Because the mismatch could signal something very interesting. But what it could signal depends, right? We don't know what it's going to signal. So for example, there was a deviation that was measured in the orbit of the planet Uranus, right? And there was a real panic about it, right, in the 1800s. because Newton's laws were sacred, and this looked like the orbit of Uranus does not match the prediction from Newton's law. There was a French mathematician, astronomer, Urbain Le Verrier, very clever man. He figured out that, Newton's laws are intact. What's really happening is there is a body beyond Uranus, which is Neptune, the planet Neptune, that is causing a bit of a perturbation, a slight anomaly in the orbit. So he actually predicted where Neptune should be. They went, they found it, and there we go. Bingo. Newton's laws were intact, right? So here was a gap, an anomaly, which doesn't fit the theory. And it turns out that what you needed was just a refinement of the theory. The theory was intact. Similarly, the orbit of Mercury also had a little perturbation. It didn't quite match Newton's predictions. Same idea. Urbain Le Verrier said, oh, great. You know what? Same solution. There's another planet called Vulcan between the Sun and Mercury, and that's causing this perturbation. People went and looked for it, a solar eclipse, and some people said they saw it. There is no Vulcan. And the reason for that is the solution for the slight anomaly, the anomalous precession in the perihelion of the orbit of Mercury, was that you needed a brand new theory. You needed Einstein's theory of general relativity, which completely reformulated gravity away from Newton's conception, was needed to explain that anomaly. Okay? And what we know now is that Einstein's theory of general relativity is not complete. It's an incomplete theory. We know that already. It hasn't been married to quantum mechanics. We don't have a quantum theory of gravitation that can explain gravity at a quantum level up to cosmic level. We don't have such a theory. Okay? And we believe that there should be such a unified theory. Okay? So when we now find mismatches between theoretical expectations and data, we don't know if we are in the Neptune situation or we are in the Mercury situation, but it's pretty exciting either way. So anyway, I'll just stop here. And thank you so much for your attention, and I'm happy to answer questions. Thank you. Oh, you have the movie? Okay, cool. Do you want to switch?
If you'd like to.
Yeah, absolutely. While we get organized with the questions, I think Frank found the movie that I was trying to show you of the orbits around the black hole of the Milky Way. Number one.
Okay, so.
It's just awesome. This is one of my favorite movies. This is real data. So.
I'll play it again.
What telescope is that from?
Keck, the Keck telescope. And using adaptive optics. So lots of clever techniques, see through the dust in the inner regions of our galaxy to make these orbits.
What time period?
So you saw that from 1995 to 2016 for about a 10-year period. Yeah. Do you want to go back to the beginning one more time, Frank?
One more time.
See that? Yeah, 95 to 2016, about 10 years. 20 years, yeah, oops, yeah, 20 years.
Okay, so who has questions? I see one way in the back up there.
Yep.
Always good to get the people in the back.
Pardon?
Are there any theories that have attempted to merge dark matter with Big Bang theory? In other words, is there any way to tell, or are there any theories that kind of try to figure out when dark matter starts to show its influence?
Oh yeah, we know that. So that's already part of the standard theory. So the Big Bang model,
Priya, we need to.
Okay.
He's gonna. He turns when we have questions from the audience. He turns on the audience mic,
Oh,
so
okay.
you have to stay away.
Okay,
Second
I'll stay
thing
away
is
from
we
that.
need to repeat the question for the folks in the
So
webcast.
the question is that is the idea of dark matter integrated with the big theory of the Big Bang, and do we know when dark matter comes into action, springs into action in the universe? We actually do. That's all part of the standard lore. So we actually know when, if the dark matter particle is indeed this cold collisionless particle, given how much there is, we actually know when in the universe it likely formed, how much of it formed, and how it actually assembled, because dark matter structures the entire universe, so we know how all of that works out with computer simulations.
Okay, the blue there.
Thank you. a good point. So there are a lot of degeneracies in that solution. So what we actually do is we have a slew of best fit models. So there's a range of permitted models, and the more data you have, the more constraints that you have, and the more you can narrow down on the family of potential models. But what I've shown you here, what I showed you, the little lumps and valleys that I showed you, are for the best possible fit of class of models. So those are sort of the unique common features that you get in the best fit class of models. It's a great question.
Okay, let's go down here to the young man on the end.
Aren't there different types of black holes? You know, one's just like positive, negative charge, spinning, not spinning.
So that's a great question. So mathematically, the question is, aren't there different kinds of black holes? Don't some black holes have charges? Aren't some black holes spinning? He's absolutely right. So we think that the basic properties, remember the mathematical solution for a black hole? So a black hole basically needs 3 numbers to quantify its general properties: its mass, its charge, and its spin. So that's mathematical black holes. As far as astrophysical black holes, we know that they are probably spinning, and so we have some evidence from X-ray data that black holes could be spinning, and we know they have mass. As far as we know, there's no evidence for charge in astrophysical black holes. But yes, black holes in general could have those 3 properties.
Okay, other questions? I see in the back there.
Does gravity have a speed of propagation?
Speed of light.
Is it instantaneous?
Speed of light. Yeah. And that was the fatal flaw that stalked Newton for the longest time. Because Newton thought that gravity, the attractive force of gravity, would be transmitted instantaneously. Einstein came along, and his theory of special relativity showed there was a cosmic speed limit. Nothing could exceed the speed of light. So yeah, it's the speed of light.
So we've got a question way in the back there. There's a
So the mathematical solution, actually, so Einstein presented his theory of general relativity, which predicted his field equations. He came up with these equations, the theory of general, 1915 in November. He gave a bunch of lectures. And so Carl Schwarzschild, who was an astronomer and physicist, a brilliant man, this was 1915, was World War I. He was in the trenches. And within a few months after Einstein had produced this theory, Schwarzschild found an exact solution, mathematical solution, the solution of the black hole, which is the point mass. And Einstein didn't believe him because he didn't think the equations are so complex. He didn't think there should be an exact solution. He thought maybe there were approximate solutions, maybe, but so the solution was found already by 1916. So science fiction got onto the act only after the mathematics came. But the conceptualization, right? So the visualization of what all fancy stuff a black hole could do, that definitely came from science fiction. So there's a slide that I didn't show because I thought one of you may ask me that, but I thought you may want to know a little bit about the wormhole. So once again, it's a mathematical solution.
And I will note that as one of our questions online, is the black hole the same as a wormhole?
No, so the idea is that, where do you go? When I keep saying, puncture in space-time, puncture, where do you actually go? Mathematically, where you could go to is to another universe. So you'd have a portal, you could go somewhere else, right, to another alternate universe. And that solution of that connection of going from a black hole in our universe, then you could connect up to another universe. There's another black hole. And that patch is called a wormhole. This is mathematics. Unlikely to find a wormhole.
Okay, I saw your hand next.
You said you get close to the event horizon of a black hole, you said time slows down.
For an observer who's sitting outside.
Okay. So if you're observing an object falling through a black hole, it seems to take forever.
Yep.
Okay, so as far as I know, no human being has been near the event horizon of a black hole.
No, and I wouldn't want to go near the event horizon of a black hole, partly because, let me tell you that, right? So.
Yeah. My question is, so when you're observing this apparent time dilation, are you sure that's not just light distortion, or they've actually confirmed time is slowing down near this event horizon?
We know, I mean, this is a mathematical calculation. It's not an experiment, right? So, but we know from the equations, from the space-time, the Schwarzschild metric, the shape of space right around a black hole, we can actually calculate how time actually slows down, and it does appear that time does slow down, and that it's a real effect, and that you may think that can I make this effect go away if I move into some other description, some other metric? Can I move into a different coordinate system? So it turns out that the event horizon, that's a coordinate system. When I can choose a system, a coordinate system to describe where I can get rid of the event horizon, but I can never get rid of the singularity. And as long as you have the singularity, you have all these effects that are real. So, and I wouldn't want to fall into a black hole. So in a way, right, you might have heard that you get spaghettified as you fall. And the reason for that, right, is suppose I fall head down into the black hole. Well, I wouldn't want to. I like my hair a little too much. But anyway, let's say I fall in head down into the black hole, right? Then the difference in the gravitational force, the tidal force between my head and my feet is what's going to stretch me out. Like the difference as I am falling in, the gravitational field is so intense that the differential between my head and my toe is what stretches me out. So I get infinitely long stretched out into a spaghetti.
I will note that your question was about measuring time dilation. We have measured time dilation using atomic clocks and flying them and getting outside just
not for a black hole, but around the Earth.
Small amount out of the gravitational well of Earth.
Yeah.
We can measure the gravitational time dilation as well as the special relativistic speed time dilation.
GPS works on that, but not for a black hole. We
Not
don't
for a
have the
black hole.
measurement for a black hole, but we have that for other masses like that of the Earth.
All right, and I saw your hand next.
What is dark energy?
What
I don't
is-
know.
That's a Nobel Prize winning
That's a
question.
Yes.
That is.
The
What is dark
nature of-
energy?
Yeah, right. I know. I wouldn't be walking to Stockholm, right? I wouldn't be doing that. So we think we know what effect dark energy exerts in the universe, right? So we know that it's this mysterious force that is causing the accelerated expansion. Just as when you're driving a car, in order to accelerate, you need to press the gas pedal. You need to give it fuel, right? Similarly, to explain what might be powering the accelerating expansion of the universe, we think it's this kind of it's a force, it's this dark energy, it's a repulsive force because it's causing the acceleration, which is countervailing the force of gravity. And at the moment, we believe that this could just be a property of space itself, that there is some kind of latent energy in space that causes this, and that it kickstarts at some point. It starts to dominate at some epoch when it starts to really pull away.
You're talking about quantum phenomena, though.
We don't know. No, I'm not. I'm just talking about macroscopic effects that dark energy exerts. So the way we discovered the existence of dark energy was looking at the brightnesses of supernovae. And we inferred, looking back, the supernovae appeared to be fainter than they would be if the only dimming was because of the distance. The fact that there was an additional acceleration caused them to appear a lot dimmer than they would with just that. And that's how we inferred. In fact, the discovery was made by a team of people, one of whom is actually a classmate of mine from MIT, Adam Rees, who works at the Space Telescope Science Institute. So they discovered the effect of dark energy. And they inferred that there has to be this thing, this mysterious repulsive force that countervails gravity. What it is, nobody knows. There are all kinds of ideas, all kinds of crazy ideas. I mean, there's nothing, I say crazy only because nothing convincing has happened. And we remain open-minded to see what it could be.
All right, well, one last question there.
Yeah.
From the perspective of a falling object, does that mean it takes forever, that it looking like outwards? Would that mean it would look like it's taking forever for the entire universe? Like times, would it look like
I don't understand
All
the
right,
question.
so I think the question is that, all right, from the outside, watching something fall into a black hole, it takes an infinite amount of
More time, right?
What would it look like from the perspective of if you were to get spaghettified and fall into a black hole? What would your perspective on the outside part of the universe be?
Well, you
Is
can't
that-
see the outside. You
Yeah.
have no information about
Certainly when
the
you get to
outside.
the edge of this, you can't see anything.
So you have, once you cross the event horizon, right, you do not know what exists outside. So actually Stephen Hawking had this beautiful analogy. So this is a thorny problem. So it's a great question because you're skirting around a very deep problem that we've not solved yet, which is the idea of what happens to this information once you go into the black hole, right? So the person inside has no idea of what's outside. Once you cross, that's it, right? And so this analogy is really gorgeous, right? So suppose you have the Encyclopedia Britannica, and you are looking up the capital of India. And you look it up, it says New Delhi, you read all about it, whatever, right? Now you put the Encyclopedia Britannica in a tight box, you burn it. You keep all the ashes in that box. Not a single piece of ash is left, right? So the information that New Delhi is the capital of India is still in there somewhere. We just don't know how to retrieve it. We don't even know how to talk about the information, right? Once the Encyclopedia Britannica has been burned. So in a way, there's some many thorny problems unsolved about what is happening to the information once you cross the event horizon of a black hole. So, I don't know, you might have heard in the press, it's called the firewall or fuzz. So this is something you can go Google. So there have been endless arguments amongst physicists about what's really going on. And there have been some interesting breakthroughs in our understanding, but it's an unsolved problem at the moment.
Okay, so I've let it go on a little longer because we've got such a great crowd and it was such a wonderful talk.
Thank you so much.
But we have to cut it off. Give her a great hand. All right. And we'll see you all here next month. Thank you all for coming.
Yeah, and I'd be happy to sign books if anyone wants to. I'm happy to wait around. Yeah, thanks. Is it okay?
Excellent. Excellent.
Thank you. It's real fun. Great questions.
Yeah, we have. Yeah, there's surprise sometimes because it's a weeknight.
and it's
It's
late,
weeknight doesn't finish till 9:30. Yeah. And who else is back there? All right, and the OPPO team that's back there taking care. All right. Okay. Good evening, everybody, and welcome to the Space Telescope public lecture series. I'm your host, Dr. Frank Summers of the Office of Public Outreach, and it is my pleasure each and every month to welcome you, or at least the months that I'm not traveling. Tonight, we have a lithograph of the pillar in the Carina Nebula. This is one of the early release observations from the Servicing Mission 4 back in 2009. So I guess it's been 8 years. Wow, it's been 8 years since Servicing Mission 4. If you would like to learn about it and see an infrared version of the same image, you can read about it on the back of these. They're available on the two tables. Please grab one on your way out if you didn't get it on the way in. Our speaker tonight, Priyambada Natarajan, Mapping the Heavens, the Radical Scientific Ideas that Reveal the Cosmos. And as I've told you the past couple of months, I'm really excited because we have no budget for this lecture series, and when I can get someone to come in from Yale, it's absolutely fantastic. So getting an out-of-town guest is a special treat. Please make her feel welcome tonight. Next month, we have Lauren Corliss from Johns Hopkins, and she still has not told me her title. I sent her email yesterday, and I haven't gotten a response. So the topic is to be announced, but she assures me, yes, it's on her calendar. Yes, she's going to give a talk. Some people had take a while. They want to wait till the last minute. They don't want to commit too early to a topic. But Lauren will be speaking next month. In April, David Law will be talking about integrated field unit spectroscopy. And I know that sounds geeky, but it's a really exciting field in which we're opening up new frontiers in astronomy. Maybe I'll have him come up with some flashy titles that'll hide the fact that it's about a technology that is just going to it really does change a lot of what we can do in astronomy. It really takes us out into another dimension in astronomy. In May, Mia Bovel, she gave a talk last year, and she'll be coming back. And it's got a period of about 16 years. Okay, if you just take this motion over the course of 1 year and extend it out, it would actually rotate all the way around the star in about 16 years. Right? That can't be something out at this 60, 70 AU distance. It has to be in something really, really in close. So what they think they are seeing is the shadow of a tilted disk down in the center, a shadow across the outer disk from a tilted disk in the center. And here's an artist's illustration of that. Oh, I'm using the wrong clicker. There we go. All right. So this is not to scale. This would be a disk way down deep, around 1 AU in size, okay? And if there were a planet tugging on that, etc., with that to pull it out of alignment, then the shadow from that disk, probably not as tilted as shown here in this artist's illustration, would actually extend across the outer disk. And if there's a planet there to precess that disk, okay, as that disk precesses over 16 years, that shadow will move across the outer disk. All right. Again, this is an explanation based upon the data. We don't have proof of this yet because even ALMA can't see down below 1 AU. All right. So this is the supposition is that there is a 1 AU, but it gives us something really cool to shoot for in this nearest of protoplanetary disks. So who knows what planets lurk in the heart of TW Hydrae? Only the shadow knows. Yes, I really said that. All right. Number 2, our second story tonight. A smidge or two of dust, gas, and star formation. So when I talk about smidge, it's in capitals, so you know it's one of these science acronyms. And this science acronym stands for the Small Magellanic Cloud Investigation of Dust and Gas Evolution. Yes, we scientists come up with some tortured acronyms, but you know, it helps us be able to differentiate our projects. All right, so this is the Small Magellanic Cloud, okay? And you can see some bright gas in here. These red little nebulae, those are bright gaseous regions, okay? And you can see that gas. But what about the most every Friday night? Please check their website and get over and enjoy it. All right. So now my favorite part, news from the universe for February 2017. Our top story tonight, only the shadow knows. The older folks in the audience get this, okay? The young kids like you, no, you have no idea what I'm talking about. All right. But maybe you still won't have an idea after I'm done with this, but it's all right. So what we're talking about here is this amazing, oh, can we kill the front, the down can lights? This is, we need darkness on the screen here. There we go. The ones that are shooting down on top of me, just kill those. Nobody needs to see me, okay? Just they need to see the screen. All right. So this is absolute amazing image. This is TW Hydrae. This is a disk of material around a almost sun-like star. It's a 0.8 solar mass star here, okay? TW Hydrae. And this is a disk of material around this young star. This star is about 10 million years old. And what you see in this disk, you also see grooves, sort of like a phonograph grooves, which of course the kids don't know either, but these are gaps in the disk around it. And this is from the Atacama Large Millimeter Array, otherwise called ALMA down here. And using millimeter wavelengths, they're able to see disks of material around these young stars. And in these disks are where we expect planets to form, okay? So we're getting amazing views of planetary systems information, not only from Hubble, but also from this millimeter array. And they were able to get the highest resolution ever of a protoplanetary disk when they looked on the interior, and they tell me they're seeing details as small as 1 astronomical unit. And 1 astronomical unit is the distance between the sun and Earth, okay? So they're getting resolution of another solar system down to the scale of the sun-Earth distance. This is really, really cool, okay? So ALMA has been doing some amazing things. They released another one that was really wonderful, H.L. Taw, is it called? Oh, I can't. Yeah, H.L. Taw. H.L. is a very good speaker, and she's talking about the Harvard computers and the HR diagram, where the word computers should be in quotes, because these, of course, are the women who processed the spectra up at Harvard, okay? And they were called the Harvard computers, okay? All right, if you would like to find out the information, you can go to our website. If you just use your favorite search engine, Hubble Public Talks, you will find us. It has a list of the upcoming lectures. It has links to watching it live or watching in the archive on YouTube or via the STSCI webcasting. And you can also sign up for the announcements, the once or twice a month that reminds you of the upcoming lecture, okay? Those announcements, you can sign up at the website. You can also sign up at maillist.stsci.edu, but why would you? It's so much easier to go at the website. Or if you are really lazy, you can just walk up to me tonight and hand me your email address, and I'll make sure it gets added. All right, we have lots of ways for you to find out about this. Actually, since we added it to the website, we have like over 300, 400 people on our mailing list now. It started out as like being 70. All right, so there's lots of people who are finding out about all these talks, and I'm very pleased to say that we're growing by leaps and bounds, at least in one dimension. If you'd like to ask questions, if there's something that we are doing wrong or that you have an improvement or there's a question you have for things, you can send it to publiclecture@stsci.edu, and one of us will get back to you with a response. Our social media, as usual, Hubble is available on Facebook, 2, not 1, but 2 Twitter feeds, Google+, Pinterest, and maybe some others that I don't know about. Myself, I have a blog on Hubble site. I'm on Facebook, Google+, and Twitter, although as I caution every month, I only do that once or twice a week because I got so much other cool stuff. There's so much cool stuff in the universe, it's hard to get to Twitter as often as some other people get to Twitter. I don't know why. At least I have more important things to do than Twitter all the time. All right. The observatory will not be open tonight because it is cloudy. I'm sorry. If you looked up and you saw the moon, you saw a nice haze around the moon. So the Maryland Space Grant Observatory is, however, available if you go to md.spacegrant.org. They have observing Centauri, which blew our minds. This one is even a little bit, because it's a little closer, is actually slightly higher resolution. All right. They also were able to, last September, announce that they had evidence that there might be a Neptune-sized planet inside this gap. There's a gap here that's about 22 astronomical units away from the center, from the star. Neptune, by the way, is 17 astronomical units. And that there might, due to the characteristics of the dust, there might be a Neptune-mass planet. They can't say for sure, all right? So TW Hydrae is a really interesting system, okay? Matter of fact, one astronomer said this: TW Hydrae is quite special. Is the nearest known protoplanetary disk to Earth, and it may closely resemble our solar system when it was only 10 million years old. Now that's some cool stuff to study. So of course, lots of people have been studying it, okay? And Hubble has looked at it. Here is Hubble's image from 2016 up against the ALMA image. Now I do this on purpose to show you that we're so used to Hubble having the best resolution, right? Well, it has the best resolution of any visible light telescope. When you go out to these large radio arrays, which can be huge and spread across multiple dishes across kilometers, they can actually get better resolution than Hubble can. So the millimeter array of ALMA actually has better resolution than Hubble does. But Hubble is, of course, looking at visible light. They're looking at millimeter. And so Hubble has been looking at this for several years, trying to determine, do we have evidence of planets in formation in TW Hydrae? All right? Well, here is a 2015 image, and here's a 2016 image. And the astronomers who've been studying this for years noticed that there's sort of a darkish region here, and then there's also a darkish region over here. So they specially processed it to try and pull out the contrast to see those darkish regions. And what they found was that this darkish region here sort of rotated uniformly across to here. Now, the idea here is that it doesn't depend upon distance from the star, right? If it were something in orbit, okay, then it would depend on the distance from the star. It's moving uniformly at many different distances, okay? And that it stretches out across here